So we have, this is 30 minutes to get through my slides, and that's cool. We're going to do this together, right? Right on. All right. So I'm Patrick McFadin. I'm now Chief Evangelist. That's kind of a new thing for me. I also do data solutions for DataStax, and so because of that, I get to work with customers. I get to work with people in open source, which is great, and I just get a lot of use cases. And part of that is, what really helps, I think, for the community is that I get a variety. And where you may have one specific use case, I get to talk to you and find out what it is. And then I can take it to the next person and say, oh, you know what? Somebody else just did that. Or maybe somebody else did something like that. So it's great because I get to talk about that. And I have some actual use cases today that we're going to talk about. So let's get into it. So first things first. As you know, data model is king. I talk about this all the time. And so with Cassandra 2.0, we got all kinds of new stuff to talk about. I've done my 3 data modeling talks, and so this is just an update on that. But it's just always getting better. We have so much that we can get out of our data models, and there's so much bad you can get in data models as well. So we have to understand the underlying storage engine sometimes, and I want to get into that a little bit today. As I talk about data models, we talk about things like using the partition keys and the clustering columns and things like that. Well, that really kind of points to the underlying storage engine, what's going on underneath, because that's the real power in your data model. It's not just creating the right field names and using camel case and stuff like that. A lot of it is just understanding where your performance is. And I do a lot of that, where we look at performance as the primary motivator for our data model. We want to make sure that it's performant and not going to fall over under load. So I want to talk a lot about that. And the topic today is going to be tuning as well. So we're going to, I'm hesitating because I'm going to dig into something today that no one else has, I don't think. And so just strap on. This is going to be fun. And we brought Elvis along with us, so this is going to be fun. So first things first, let's talk about new features. Lightweight transactions. Now, transactions are more of an ACID problem, right? I mean, if you're using a relational database like MySQL, lightweight transactions are not what you're going to get. You're going to get full transactions. But in a distributed system like Cassandra, lightweight transactions are very useful for a variety of edge cases. And distributed systems have a problem. Some of them are solved in really bad ways, such as a distributed lock or external locking system. So let's talk about this particular problem here. Here's my problem. And this is a complicated slide. The problem I'm going to have is whenever I'm creating a new user account. So a new user account, over on this side, I have one process. And this process is like, hey, here's my, I'm going to select from this user table, and I'm going to look for the existence of a user. Well, this is a read before write, which is an anti-pattern in Cassandra, right? Because you have this moment. Well, here's how it would come down. So at T0, I look for P. McFadin, this guy, who might be me, and it comes back with 0 rows. OK, that user doesn't exist in the users table. Awesome, OK. Well, at T1, another process asks the same question. Now, for that particular username, which is a primary key, it comes back with 0 rows at that time. So from T0 to T1, it could be a few milliseconds. Well, so the process 1 says, well, there's nothing there, so I'm going to go ahead and create this record. So this is me that I'm creating. This is Patrick McFadin that's being created, and writes that into the database. Well, process 2 is unaware of that this happened. And process 2 is going to say, hey, there was nothing there. I'm going to go ahead and do it too. So at T3, this guy, Paul McFadin from Oracle, overwrites my record. And that's not cool. So the sad panda, right? I mean, that's a reality that happens. It's a sad reality. It's a sad panda reality. And this is the edge case that we have warnings about. Hey, you know, this is why you don't do a read before write, because the guarantee that the next time when you do the write, that it's going to potentially overwrite the thing that wrote it before. So at T2 this was written, T3 this was written, T3 wins. Woo! Wrong record. So when I go to get in there with my username and password, it's going to reject me saying you don't exist. But I just got an acknowledgement that I created my account. That is not workable. OK, so how do we fix that? Well, I think you probably know the punchline, right? Lightweight transactions. So a lightweight transaction is going to give us, I knew I was going to trip on that. What's going to give us is this edge case solve. And this case, I go ahead and create at T0 this account, and I use if not exists. That's new syntax. Now what's cool is it's going to come back and say, you're applied, it's true. So it's going to do an existence check to make sure that it exists. That's cool. It uses Paxos to make sure that it is the one that is doing it and creating that record exclusively. And when it's applied, it says to true, and you're good to go. Well, that's good. That's insurance from the application side. As you guys know, I love writing applications. I hope you know that, because applications are what we're trying to do. I don't really, databases are just another way to store data, but applications are really where that's what is fun and exciting. But it's not fun and exciting when I have to write all kinds of crappy application code to make sure I'm not overwriting records. The database should take care of that, and it does. So in this case, I got an existing record. So what happens later when Paul comes along? Well, that's later, maybe milliseconds later when that happens. Again, our application code is written, so it says if exists. Well, now what happens is it's going to come back with a false and say, no, dude, that's gone, man. You can't do that. And that's what I wanted. That's what I really wanted when I use it, if exists. Now it's stopping me. It's like, well, hold on there. And it's not going to stomp on my record. And from an application side, that's easy to deal with. Whenever you say if exists, then I expect it to check for that and come back to me if it does exist. Now I can go back and say, I'm sorry that username already exists. Pick a new one and kick it back to the user. Exactly what I wanted in the first place. No more of this, whoops, I overwrote your record. So the fine print. So it's meant to solve those edge cases. It's not meant for everything. But you have to have awareness of what it can do. Of course, there's no free lunch. It's using Paxos. That means we're going to do more round trips. But man, it is very useful. And I would rather do it there than I would do it in my application code. I put in this shutdown Zookeeper. I've seen a lot of cages. It was a project that used Zookeeper to create this problem, where create this exclusive lock. That has edge cases as well. We're eliminating those edge cases by putting it closer to where your data is. That's where it should be. So there is a bit of a latency, and it can vary based on the size of your cluster. But I would say load test it. Make sure it's part of your system. But only use it when you need it. So what about a real use case? Right, that was cool. So if you saw my talk, my third talk on data modeling, I had this form versioning use case. And it was a real-world example. And it was almost like a setup for this talk. I'm glad everyone played along. I gotcha. Here's the punchline. It didn't work. Well, it worked, but that actually used Zookeeper to manage. And that is really making me sad. So we're going to fix that today. We're going to right the wrong. So this is from Next Top Data Model. That's what I did at Summit in San Francisco. And so the use case was there's this form versioning system that used this working version. But the idea was that we have this user-exclusive lock. So as someone is editing a form, they want to be the only one editing it. There, of course, and somebody even called me out on the questions, like, isn't there like some potential where, yes, there is, and you have to create some sort of cage around it with Zookeeper or use lightweight transactions, right? But there's a potential that this thing could get overwritten. Let me explain what I mean. You might have this problem where, and this is the exact slide I used, but there's a problem. I didn't put the danger zone in there. But when you insert the first version of this form, and you want to make sure that that one person is the only one locking that form, so when you say update this particular, this set locked by and by me, well, in between when you create the form and you update the locked by, there's this blank zone of potential danger. You could have someone come along and do it right on top of you, and that's unacceptable in my opinion. And so let's try to fix that. So when we release the lock, we may not even be the ones that have the lock in the first place. So there's all these kind of like bad state problems that they just don't want to have to deal with it. So let's revisit that problem again. So form versioning, part 2. Now, of course, there's a punchline. You use the LWT, the lightweight transactions. So what I'm going to do now is whenever I create the record, I'm going to use the if exists, if not exists, syntax. And there you go. I'm the only one creating this particular version of the form. So if a millisecond later someone else comes along and wants to create a version of that as well, because of the primary key being the form ID and the username, well, once that happens, then I'm going to be the one that's going to be the only one updating this record. And that's what I wanted. And so now what I could do later is as I update, I use this if syntax. So if my lock by is me, I'm the one doing the update. That's what I wanted, right? I don't want somebody else updating my record. Then it's going to accept my updates. If dude comes along, because there's a guy named dude, and he tries to update my version of my form, it's going to reject it. And that's exactly what I wanted. I wanted to make sure that I'm the only one updating this record. It's very exclusive. And we're managing this on the database level. It's not through like Zookeeper or something else outside, which has its own problems. So yes, this is a lot of using LWT, but it should be a pretty good example of how you should be able to use it to make sure you're the only one, you have exclusive locking going on in your records in your database. So the old way was deal with it in kind of weird ways, external locking, or I know a lot of people that just roll the dice. Hey, let's just make sure, let's see if it works. It doesn't, you do not want to go with pure blind luck and chance on things like where potentially you could have records overwritten in your database. Bad news. I've tried that. I always get bit on it, right? So now the new way is now we have a very formal way inside the database using exact language and exact syntax to make this work. Perfect. That's exactly what I wanted. So I'm going to do my exclusive locks by existence checks. I'm going to make sure the exclusive one writing the record. I'm going to use the if clause to make sure I'm the only one doing it from then on. And of course, just understanding that there's more latency involved in that. For form versioning, I'm not so worried about it. Maybe for other applications, I will. So this is when you really need to load test. I'm going to stress that because I work with people all the time. You just need to understand what's going on inside your database. And there's no magic. There's no free lunch all the time. But just understand what the load balances or what the trade-off is. All right, so enough about features. Last time I did a talk, I said, after the end, I said, you guys tweet me on what you want to talk about. So everybody wants to talk about performance. And data modeling and performance is a big topic. I do this all the time, and I love it. So let's talk about making your stuff faster. So first of all, with Cassandra 2.0, we have some changes that I personally like, and 1.2 has some as well. But let's talk about those. And what is it? So first of all is a single pass compaction. And second one is, these are 3 things that I like a lot. The hints to reduce SS table reads. And then finally, faster index reads from off heap. So those are 3 features that probably never made it on anybody's slides except mine. But that's cool, because then no one else stole my thunder. So why is this so important? Why am I excited about it? Because like I said, I work with people all the time whenever they're like, oh yeah, I just want to squeeze 1 more millisecond out of my queries. Well, there's a lot to do. I mean, there's a lot to do to get that, and I'm all about trying to get you there as well. So why is those three important? Well, it comes down to SS tables being read when you do a read, a query. It's all about how many SS tables there are involved. So reducing the amount of SS tables you read means less seeks. So just a quick review. When you do a read, it goes to Cassandra. From there, it has to go to the disk. All right? That's an important thing. If it's not in memory, it's got to go to the disk. If it has to go to more SS tables, that's more latency. So disk seeks are the evil in a read. And minimizing the amount of seeks you do on the disk is the key to happiness and fortune and speed. So I got an example here of some disk latencies. So if you're using SATA or 7200 RPM disk, really slow disk, it takes 12 milliseconds to do an average seek. That's 12 milliseconds. So if you come to me and say, I'd really like to do a seek, or I'd like to have a query return in less than 10 milliseconds, it ain't going to happen. So it could happen if it pulled it out of memory. But if it has to go to disk, you got 12 milliseconds. 10,000 RPM, OK, getting better. 15,000 RPM, a little better. And this is just rotational speed that's going to give you that seek. And you still have transport on top of that. Now, I put this on here. It's kind of like a little pepper. SSDs are awesome, right? That's 0.04 milliseconds on a seek. That's one of the reasons I really like SSDs. But you shouldn't have to rely on that all the time. So if I have to do 5 seeks to find my data on this 7200 RPM disk, that's 60 milliseconds of just disk. Nothing else. I mean, there's nothing else involved except a spinning disk and the disk head trying to find my data. So because I like to make this point as often as possible, don't ever use shared storage. Because these numbers are really optimistic for local storage. If you start using shared storage, such as NFS, you will be really, really bad off. This just happened to me. I had this happen 3 times in 1 week. It was a couple weeks ago. 3 different users, all with horrible performance problems on queries. All of them using shared storage. That's it. That was the common theme between the 3 of them. And when I mean shared storage, I mean NFS. Here's a horror story. This is a bloodbath. This is if you were at if we were at the meetup last night, I talked about this some. The bloodbath was that they were using NFS. Every seek was taking around 100 to 300 milliseconds. So whenever you're doing lots of those a second, maybe hundreds or thousands a second, it burned out. It just couldn't keep up. Because NFS has just got really slow latency. It's terrible with latency. So I'm going to bring that home a little bit because I like to do that. But I just don't want you to call me or send me an email and say, man, my Cassandra sucks. Man, this is the worst database I've ever used. I'm like, well, what are you using for storage? NFS. Well, don't call me then. You know, it's just try something else. Maybe try, go down to the, well, you don't have Fry's around here. We have that in the Silicon Valley. But go to Fry's and buy a $50 hard disk. It's probably going to be faster than that $1 million storage array that you bought. And that's kind of the sad reality. I get a lot of that. Well, you know how much money we spend on our shared storage? It should work. Yeah, it should, but it doesn't. And sorry. And I used to buy storage all the time. It was great. You know, the sales guys were awesome. They would take me out to lunch, dinner, whatever I wanted. They'd take me to baseball games. It was awesome. But it doesn't work really well for what we do. We're building distributed systems, not a single point of failure. And that's what you're building with this shared storage box. I had an EMC array. Sorry, EMC. I had an EMC array. It went down. What did it take with it? My entire Oracle system. So yes, I'm a little, yeah, anyway. Do you want me to talk about that anymore? No? All right. All right, so is anyone going to use shared storage from now on? I don't see any hands. OK, good. So let's talk about measurement. Now, I say quick diversion. All right, I'm going to go into something a little deep here. I hope you guys keep up with me. This is going to be good. I do this. I've been doing it a lot lately, and it has been really useful. CF histograms. Okay, I know, it's one little topic, right? One little tiny topic, but it is going to save your life. And let me show, well, all right, maybe not save your life, that's a little extreme. But anyway, it's going to make your life a lot easier when you work with query optimization and working with Cassandra, and just understanding what's going on. So, CF histograms are histogram statistics on a lot of things, per table. So they're collected when you do a read, when you do a write, when the SS table is flushed to the disk, and when you do a compaction. So there's just a various amount of statistics gathered about this particular column family or table. And here's the syntax. It's a part of the node tool. CF histograms, you put in the key space in the table. Now what you get out of it is this nice little setup. But whenever I put that on the screen, I've done this before, I'll be on site with a user, and I'll say, all right, let's bring up on our big screen here, let's bring up CF histograms, and it goes, boof, it goes on the screen. And I get the same look from everybody. And it's just like a wall of numbers, and I don't even know what that means. So, all right, today you're gonna learn. So just be ready, okay? When you walk out of here, you're gonna go, oh man, I'm gonna use that every day now. So, how do we do this? So this is a output of CF histograms. Very short output, but this is what it looks like. You get, when I say, give me CF histograms for my video DB key space and my users table, I get this output. And there's these really nice columns of numbers, but what do they even mean? And I think this is where the breakdown is like there's no units on one side, and then what direction do I read it? So let's go through that. So the very first column is the offset, and that doesn't have any units. It's just buckets of numbers, and they're kind of meaningless until we start going further into what next column we're going to look at. So let's go to the next column. So SS tables. Now, when we look at SS tables, we get a number here. So it's how many reads, how many SS tables it took to do the seek, okay? So the offset is how many SS tables had to be seeked to satisfy X amount of reads. So in this particular one, there was 107 reads that took one SS table seek. There were 2 reads that took 2 SS table seeks. All right? So what I'm seeing here is the efficiency of my queries from Cassandra's point of view. Like how many seeks did it have to do? If I start seeing those numbers crawl down, say if it was doing 250 seeks to find my data, there's something wrong going on here. And we could fix that, but we just need to know that that's happening. So this is how I'm getting some idea of how much disk activity it really takes to get to my data. The next one is latency, and that's in microseconds, not milliseconds, microseconds. And that's pretty easy, actually. So it took 5 writes, took 250 microseconds. 10 of them took 800 microseconds. And those are pretty typical numbers. But that way I get an idea. And these are exact numbers. This is how many, there's a one-to-one relationship. It's not an estimate. It's, yes, that's how long it took from the storage engine. Next one, pretty similar, it's read. It took 50 reads took 800 microseconds. 300 took 1,250 microseconds, or 1.2 milliseconds. So this gives you a really good idea of what's going on from the storage engine side. Now, the next one is a little more, it's a completely different unit. It's how many partitions, how many partitions and what size. So I had 5 partitions that were 1,250 bytes. Now this is really important whenever you're trying to find really large partitions which can impact your performance. Let's say, and I've seen this before, I've seen way down here, you have 30,000 1 gig partitions. Wow, that's a little slow because it took a gig of data to get all that data into, I mean, it was churning through that. Or I saw one data model where they had 1 row that was 30 gigs. I'm like, why did you do that? Well, you said create wide rows. You created 1. Yeah, okay, we'll fix that. And that really happened. It was kind of a funny moment. I was like, wow, you really did create a wide row. The cell count is how many cells are in the storage row. And that's also pretty interesting. I've had people say, I thought I was only putting 5 cells in there. How come there's 30,000? Oh, let's go back and look at your data model. Yeah, that's wrong. So this is just a way to measure what you're actually doing in your system. So what are we going to do with this? So your data model plus histograms, this is how you're going to measure this thing. So we say we test, we measure, repeat. So now whenever you create your data model and you start running some load tests, now we have a way to measure this. So let's talk about that real-world example. So this is a real customer. I've done this a lot. Real person, real user. They had a really tight SLA on reads. Actually, what happened was this guy kind of stuck his neck out. He's like, oh yeah, I could do that in 10 milliseconds. And then he came back and said, we can do that, right? So yeah, all right. So 2 days later, we did a lot of optimization and stuff, but it was a pretty cool moment because we were in CF histograms a lot, and it really dug into it. So I'm going to show you some real numbers. So the problem was that they had this variability that they needed to reduce, and every time they loaded data, it increased the amount of latency that they had. And this may be a problem that you've seen before. Hey, I just loaded up my system, all of a sudden my read latencies are horrible. So real CF histogram. Sorry for the wall of numbers, but one of the things I do with CF histograms sometimes, I don't actually look at the actual number. I kind of back up a little bit and fuzzy vision it a little, and you see lumps, right? So you see this nice lumping in the middle here. Well, that shows you like where most of this stuff is. Now the tighter it is, that's good. The wider it is, that means you're getting just this big variability. So that's the fuzzy part of it. But what I'm also looking at is most of these requests, these are read requests, were in that 600 microsecond to 4.7 millisecond range. So okay, that's what the number is. We were trying to tighten that up a bit. But the problem here is, look at the top. It was going down to 4 seeks to get to my data on some of those. Now, it didn't go over 4 seeks. That's cool. That's what I was hoping for. I mean, I've seen it really bad into 20, 30 seeks to get to my data. But I knew that really the key here was that whenever they were loading up all their data, we were looking at compactions. And compactions were falling behind. And when compactions fall behind, it makes it so that your statistics are bad, your Bloom filters are getting a little stale, and it's just going to take more seeks to find your data. So yeah, they had disk I/O problems, and so we kind of did some work on that. And the focus of that particular tuning exercise was, all right, let's tune up your disk and make it so your compactions keep up. Good. So we did that. Boom. We got that kind of straightened out a bit. We got better compactions. We weren't falling behind. And we actually eliminated an entire seek. Look, it's gone. This has never happened again. So the max was 3 seeks. All of those numbers went up by 2 milliseconds, which was awesome. And you could see the causality. You can see that, hey, we took away that 1 seek and the whole thing just bumped up. And so we started really seeing those numbers come out, and we did a lot more tuning on top of that, and we got these much better. I have the final numbers. So what about this partition size, though? That was another thing that we were looking at, too. All right, so they're about 6K, 8K of data. So okay, it wasn't a lot of data. So we were going to manage that as well. So on the partition size, we looked at tuning this as an option, and because it was a size in bytes, and it's all about those reads. So I'm just going to touch on a couple of things here, and I don't want to get into this too much right now. I am going to do a talk on performance tuning exclusively, and we'll go more into this. But this is another couple of things to explore, is your index interval. And the index interval is the samples that are taken whenever your data is written out, whether or not it creates an index or not. And so sometimes in certain use cases, you can lower that for faster access. But what happens is you're creating more index, and it uses more memory. So the trade-off is you're using more memory, but you do get faster response. So that was one of the things we kind of tweaked with a little bit. The column index size, when it adds indexes to those columns as well. So if you're doing a lot of partial row reads, maybe making it smaller will index that so you get to your seeks faster. That was another thing to try. So after we did all that, we got some really good numbers. And the biggest deal was this percentile. You know, I'm big on P99, P95, 99th percentile, 95th percentile, because that shows what you should expect. That shows variability, whether or not you have variability. And we had 9 milliseconds in the 95th percentile. This is production data. This is live system. This isn't under a load test. As they're getting, as their system is being hit by real users in the real world. And they're doing 10,000 transactions per second at peak, 220 million a day. So this isn't a bored system, you know, and we're doing 9 milliseconds, 95th percentile. That was awesome. But it really came down to just because we understood what the problems were, and we were able to measure that. And that's really the key. Just knowing what knowing what the problem is, you can solve that. And there were little things. I mean, I could tell you all the million things that we did, but your use case is going to be different. But just know that's where you go to get data. You go to look at your CF histograms. That is going to be a great tool in your toolbox when you're tuning your data model. So what did we do? We played around with the index interval. We wound up lowering it because they had these small seeks, and then same with the column index size. And then we upped the concurrent readers. They had enough bandwidth because they're using SSDs that we could increase the amount of readers. So these are the 3 things we did for this particular model. And it actually, by making compactions work better, changing these 3 values, and measuring it very well and with the CF histograms, we got a pretty good, I mean, that's pretty good, right? I would be pretty happy with that. Actually, I was. So here's another thing I'm going to throw out one more thing to look at. The 2-hump problem. I call this the 2-hump problem because I see it all the time. Thank you, Ruth. The 2-hump problem is, hey, I got my read latency looks awesome, except for right now. You know, you see these, what is that? It's compaction. Again, disk I/O, or worse, something else happening on your disk. So, which is something I have to point out because this shows you that you have disk latency somewhere. That everything is cool right up until something else impedes your disk. And then you'll see it, and granted, these are not crazy numbers. There's worse numbers out there. This just happens to be one particular user that I had some data from. I collect these things like baseball cards or something, you know. Hey, can I have your CF histograms? Thanks. I won't put your name on there. If you want to send me yours, great, I'll collect it. What we did is we throttled down compactions on this particular one because they weren't really falling behind, but what happened was they were just letting it go crazy. So we throttled it down a little bit. We did some disk tuning. But I mean, the other thing is you can just ignore it. And this one, I would ignore it. 535 microseconds for a read. Who's going to cry about that? That's amazing. But in this case, you just know that there was some impedance on the disk. And I think it's probably more expressed because of the really crazy low numbers. Most of that data was being served out of memory anyway. That's what those numbers show me. So anyway, that's the 2-hump problem. So wrapping up here. So I hope that what I showed you is there's this, there's data model, but then understanding it. So understanding those internals are really, really important. If you haven't seen my talks about some of the data modeling techniques and like how slices work, how using the partition keys, how they can help you with your data model, that's what I'm talking about, is the internals. But there are a lot of good talks on Cassandra internals. Anyone that Aaron Morton does, I mean, just put your thinking cap on because they're pretty heavy. But he talks about these internals, and I've used his blog, The Last Pickle, so much on just trying to understand like what is going on in the internals. If you want to become like a supermodeler, crazy good at query tuning, just understanding a bit about how the storage engine works will really help. So the other thing is, boy, the disk is the #1 problem when it comes to, finally, when it comes to your data model. Because you could build the best data model in the world and put it on crappy hardware, your NFS. Don't do that. I already told you, don't do that. Because then you're going to be hating yourself because you think your data model's wrong. But it's not. Your data model's great. It was just that you have it running on horrible hardware. And you can find that out by learning how to measure a sea of histograms. I would go out and try it on your own systems. Try it out. It's really easy to see and use. And I bet you everybody who's running a production system right now is probably logged in. That dude right there, he's doing it right now. Yes, is he? All right, cool. He's like, oh man, we got the 2-hump problem. Yeah, everyone's gonna walk away here and going, I had the 2-hump problem. And then load test your data models because you won't see those problems until your system's under load. You could do traces. Traces are great, but when your system's under load, those are when things come out. So understand that. So that is my really short talk. I hate having 30 minutes, but I have a few minutes for questions. Here's my other 3 talks. If you haven't seen those, check them out. They're hopefully very helpful. And if they're not, then I'll do more. So I'll go ahead and questions, anyone? Yeah?
What about cloud installations? When one disk is used by one disk block is used by several virtual machines?
That is a recipe for disaster as well. Because what you're doing is you're impeding access. If you get down into disk internals, it's going to be about what the disk head is doing. If you're using spinning disk, you have a head that's sitting on top of a platter and it has to move around. If one system asks for the disk to be here and the next one wants it over here, there's going to be swing latency. It's just physics. If you're using SSDs, it's not as big of a problem because there's no longer a disk head movement that actually has to occur or rotations that have to be met. But impeding on the transport is probably way more important at that point. Like, I don't want to just throw out random tuning techniques, but your scheduler that you're using in your operating system is probably not correct. Like, if you're using Deadline or NoOp, you're probably going to be better off than using something like CFQ. Your mileage may vary, of course, but the transport is going to get in the way. If you have multiple systems all nailing that transport at the same time, you're going to back up and you're going to have trouble. You're going to see the 2-hump problem because of somebody else. Yeah. Yeah. More? Yes?
I'm thinking of using your lightweight section for rollover, but the difficulties when it comes to releasing the logs if an application dies, for example.
Right.
And how I would apply a log. There are 2 processes contained in place.
I would ask, first of all, do you really need the lock? And sometimes it's easy to get trapped in the ACID world where you say, well, of course I'm going to do everything with a transaction, but do you really need a transaction? Sometimes, especially with logging applications, you just need to make sure that it happened. Using more of a time series model in that case means that every transaction that does occur is isolated by the fact that it's in its own time bucket. Banks use this all the time.
The use case I have is where you have like an item that people buy. As they buy it, then the number of available items has to decrease or increase depending on the case.
Right.
So there you need to have a lock on the roll.
And a potential way to manage that is to have a process that does roll-ups every so often. But you can have that process get an exclusive lock on the final count, and then use a transaction log to keep the counts rolling in that case. It depends on the speed. If it's not a speed problem, use transactions to do it, make if exists or something like that. Or not even if exists, just the if clause on transaction locking. But there's probably faster ways to do that in that case. Yep. Next, who else do we have? In the back.
These are lightweight transactions across clusters or local cluster only?
It's across data centers, and then there is what's considered local So it's just like as quorum is across data centers, or you can use local quorum for the local data center. The first class is, of course, across data centers. So it's data center aware. So, and I actually argued quite a bit about having a local version of that, and I was told no first. But now it's there. But if you're thinking about, like, if you have, like, for instance, a username that you want to make sure is the only one getting created, you have to do that across your entire cluster, no matter where it is across data centers. So that's the first way it works. Yeah. Yes?
So if one of the nodes dies, what happens?
Well, yeah, so it's durable, but Paxos requires quorum as well. So if it can't satisfy quorum, then it's not going to satisfy that level of consistency. The lightweight transactions is a level of consistency in your database. So if you only have, say, one node out of 4 that's alive, you're not going to be able to do it, because that's just not enough to satisfy that quorum. Any more? All right. Well, enjoy lunch, everyone.